looking at what we started out with. Started out with a theory which had SO2 or equivalently U1 global symmetry, and so we had a typical Lagrangian which had this form, where phi was a complex scalar field minus some u which just depended on the magnitude of these guys. Okay. So, this is a typical Lagrangian 2 derivative kinetic energy term and an arbitrary potential which has global U1 symmetry. Okay. And then the idea was to convert the symmetry into a local symmetry, and that we did by introducing the idea of introducing an extra field, a gauge field which had a specified transformation property such, and you defined a covariant derivative. Okay. And so, this theory was automatically now invariant under local U1 symmetry. Okay. So, now the question is, can we what happens if we consider some other, I mean more importantly other global symmetries. Okay. In particular non-abelian ones. Okay. And keep in mind that the symmetries we have in mind are the continuous symmetries, okay, not discrete ones. And so the canonical and the first non-trivial example of non-abelian symmetry is the SU2 group, SU2. So we will work with this example which is SU2. Okay. So we have seen this definition, or we saw that we could write this as the set of unitary matrices with determinant equal to +1. Okay. And in your one of your assignments, we have actually shown that a typical element of this G which belongs to SU2 can be written as exponential of okay. So sigma A here are the Pauli matrices, okay. And just for completeness, let me just write out all of them. This is a minus here, this is correct. I always make a mistake with respect to this. Okay. So this actually shows you that and theta a's, so theta a's are parameters, okay, parameters. But we also saw that the condition on these thetas is that they live on a sphere, 3 sphere. Okay. So theta a's are parameters, or we saw that coordinates on a 3 sphere. So, all these features are actually kind of generalized to any Lie group as we saw. So, just a remark, for any Lie group okay, we could write G as some e power I okay. Maybe I should be little bit more pedantic and write upper and lower out here, and where A will run over the to what we will write as dimension of G okay. So, this is an example. So, the dimension of SU2 in this case is 3 okay. It is just roughly the number of parameters that you need okay. And one more thing we saw is that the Lie algebra. So, these are the TAs and TAs are generators of the Lie algebra. So, coming back and mapping, looking at this, we can see that T for SU2, the TA that we have chosen here is half sigma A. The half is part of the normalization okay. And it is easy to show from, one can show that the Lie bracket, but in this case we saw that once you write it in terms of matrices, the Lie bracket is nothing but the commutator. So, the Lie bracket of these guys is equal to I epsilon A B C T C okay. And this is an example of the structure constant. So, I have to be really precise if I want to write things correctly. Did I write it with an upper A? So, let me just be more correct and write this is I was not consistent from here to here. So, let me be consistent. So, theta A is upper and the TAs are lower. So, then I need to do less work here okay. So, this is what you get, and so we know quite a bit about this, and the nice thing about SU2 is that it captures the complexity of all non-abelian gauge groups. This is a nice thing. So, what we will do now is to write something which has SU2 replacing U1 and just push this through and see what we will get okay. So, the goal is start with a Lagrangian that has global SU2 symmetry and convert it into one that has local gauge symmetry. This is the goal, and more or less we can follow these things through, but there is some nice thing one nice thing to see is that suppose we considered a particular only a situation where we are looking at the subgroup with only one theta turned on. Let us just okay. So, just for simplicity consider the subgroup with only one theta A non-zero. Okay. So, with no loss of generality I can choose that to be theta 1. I mean I just choose one of them, but in principle I can do it for every one of them. So, I am just right now choosing one particular example. So, first thing is what is the group generated. So, the question is what is the group. So, the group okay, it is a bunch of elements of this form. Let me, so in this case it is, why am I writing this? So, let me be even more, so let me choose, okay, theta 2 equal to theta 3 equal to 0, being too general. Okay. So, I have theta 1 sigma 1. Okay. What does this group look like? What is this group? SO2, it is just a rotation, it is a U1 or an SO2. So, this is in fact, if you expand it out, you will see that it has cosine thetas and okay. So, I will not, it will be some 2 by 2 matrix, okay. Sigmas are these things. So, it is just a U1. Now, you can see that now, so what I can do in my mind at least to say okay, first step I will do is to consider this global symmetry and try to make it local, okay. And then it then this looks exactly like the problem we have already solved. We have already solved this problem, okay, modulo some details of working things out. So, the thing is what does this tell you, that for theta 1 I should introduce one gauge field. Now, I can repeat this thing by saying I do not look at now the thing is invariant under theta 1. Next step I do is let me ask, can I make it invariant under theta 2? Theta 2 is not switched on, and theta 1 and theta 3 are 0. Again, it is not hard to see that is also U1 or SO2. So, again it is the same story. So, you can see for every such parameter, even in the most general case, we have for everyone we can start looking at different U1 subgroups, and you can scan through the whole set of these guys. And so, what does it tell you? It roughly tells you that if you need to, so the conclusion by looking at this to, so let me write this, to obtain a local in U1, let us call this U11, U11 invariant Lagrangian from the global one, of course. So, if your theory had full SU2 symmetry, obviously any U1 subgroup also is invariant, okay, from the global one. We will need to introduce a gauge field or a vector field, which we will call A mu 1. The 1 is to remind us that this has to do with the theta 1. Okay. So, at least the guess based on this is that we will need 3 gauge fields to write out a locally SU2 invariant Lagrangian. What is the constraint? Oh yeah, okay, there is a constraint, yes, but the key point here is let's look at, let's assume that theta is very small just for a moment. So, what that is telling you, if you pick a particular point and you are looking for changing thetas in that neighbor, okay, there are 3 independent parameters, okay, that is all that matters. S3 has 3 independent parameters, and this is also S3, because usually what you do is write it as theta a. So, you write it as theta 1 square. I mean, this is not the way to show that it lives on a sphere. These are not the coordinates for which square to 1, right. These are not the ones, it is something else. Okay, we showed it in a different manner, but what I am saying is that does not matter. That is why I just call this theta a's coordinates. These are not the coordinates you get by starting with that. You would start with 4 such things. S3 comes by taking 4 coordinates and putting a constraint. But here, so these are exactly the same number of parameters as you have coordinates on the thing. So it is well, it is not overkill, even that way. So it is consistent with the constraint. Okay, and I am not saying this is only a guess, but this is a good guess. Okay, and we will see that more or less this goes through. Okay, and I will not follow this route. I will follow the route that I just straight ahead go ahead and turn on all thetas. Okay, but intuitively, even before you start, you should realize that you will have as many gauge groups as the dimension of the Lie algebra is 1 for every theta. Okay, so let's go ahead, and first step is to write the most general globally invariant thing. We will use the same setup. Okay, so except I will redefine what I mean by phi. So let's it is important to realize that here what I have used G here, this is a unitary realization of this thing. Okay, and we will always assume in most physical literature, we always assume that we have a unitary realization of the group. Okay, for SU2 itself, you could have instead of writing this, I could have written a 3 by 3 representation. That would be a normal rotation matrix, which is the same as an SO3 matrix. But I could have also done something like 4 dimensional one, which is like spin 3 half, I guess, right, 2j plus 1, yes, spin 3 half would be 4 dimensional. So here I am just choosing something very, very special. So this should act on something which is 2 dimensional. So I will just choose phi to be a 2 component complex object. Okay, and under SU2 transformations, phi goes to phi prime, which should be just G dot phi, where G is what I wrote out somewhere there. So this is equal to okay, and so this is a multiplet okay. So the correct state, the one states that one says that phi transforms in the 2 dimensional representation of the Lie group SU2. Okay, it has many other representations. If it was in the if it was in the 25 dimensional representation, then phi would have 25 such things, and we would not use the Pauli matrices, we would use the one suitable for that. We would use some 25 by 25 matrices, which satisfy, however, satisfy the same Lie bracket, the bracket structure. Okay. So in your assignment you will see things done in more generality, but I always find it useful to keep this SU2 example in the back of my head. Whenever I get a bit confused, I just say, put it out there, and then it sort of explains things. Okay. Yeah. So now so we have a field like this. So we just need to make sense of this. This is where the mathematician's way of thinking of star as dagger helps. But since we are not we are physics people, we write, let's replace it by a dagger. Okay. So now we need to know how does phi dagger transform. Phi dagger actually transforms in the complex conjugate representation. Okay. So phi dagger, so okay, so you do it this way. So you are given that phi goes to phi prime. So phi dagger should go to phi prime dagger, okay, which will become phi dagger dot G dagger. Okay. And since G is unitary, what does that imply? G dagger dot G equal to 1. This is just the unitary property. Okay. So, now we so the idea here is to go ahead and construct objects which are invariant under this thing, under the SU2. So, the first invariant we could write. So, SU2 invariants, let us go, okay, constructing SU2 invariants. Okay. So, I want you to give me some examples of objects which are invariant under the SU2, starting with the field phi. Of course, you are given this. So, can you give me some example? Phi dagger phi. So, first obvious guy is phi dagger phi. Why is that? So, let us put primes out here and look at how this these two things come. So, this is equal to phi dagger dot G dagger times G dot phi. Okay. And the unitary property of G implies that this is equal to 1. Okay. By the way, this is true for any all representations, like I said, we will always choose them to be unitary. Okay. The group need not be the unitary group, even this could be SO3, it does not matter, it could be SU10, it does not matter. Okay. So, this kind of object will always be invariant. Oh, this is prime is correct. Okay. So, G d dagger. So, this is equal to phi dagger phi. So, in fact, you can see that any function of this, okay. So, more generally any function of phi dagger phi, or let us call it u itself, is obviously invariant under SU2, nothing needed. Okay. This is kind of nice, you can see that with this structure it looks exactly like what we did for the U1, except for the U1 we chose phi to be one component. So, it becomes a special case of more general things. Okay. What about now looking at derivatives, how does d mu of phi prime transform? Okay. D mu of phi prime, this is a local I mean this is a global thing. So, this is equal to d mu of G dot does not act on anything else. Okay. So, what this tells you is that d mu of phi prime transforms exactly in the same representation as phi, same exactly like phi. Okay. So, now question is, can we construct Lorentz scalars, so Lorentz scalars from this object which are also SU2 invariant. So, can you give me something? Can we construct an invariant from this? Yeah. So, the kinetic energy kind of term you can check, again the same thing goes through. Of course, a scalar plus SU2 invariant. We are only talking about global, so there is nothing. Okay. So, now you can see that now the whole Lagrangian which I just erased out here works with just one change, that I did write phi dagger instead of just phi star. Global SU2 invariant Lagrangian density is and it is invariant by inspection, we do not need to do anything. Okay. So, now we have to clearly do the next step. Okay. So, now making it invariant under local SU2. Okay. So, now we have what happens is that G is a function of the coordinates. Okay. So, the way we make this depend on space time is to require that the parameters become x dependent. The sigmas, poly sigma matrices just go for the ride, I mean they keep track of the matrix part of the group, I mean the group theory part of it. It ensures that it is indeed a unitary matrix without, and this continues to hold G dagger x dot G of x is always equal to 1, the identity. It still, it does not depend on whether theta is constant or depends on this thing. Okay. So, in other words, what this tells, or one more thing, we can go back now and look at this Lagrangian and ask what happens now under local transformations. Again, this is very easy to see that the potential term is all continues to be invariant. Okay. So, the easy part remains invariant under local SU2. Okay. So, but the problem will be we have to revisit how this transforms now. Okay. So, we need to work out. So, let us look at d mu of phi prime. Okay. Again the transformations are exactly as before, except we will put for local we just say G is G of x, okay, and similarly out here phi prime transforms like G dagger of x. So, there is nothing more. So, we have to write this will be d mu of G dot phi. Okay. So, it has one part which is nice, which is when d mu acts on this is as before, okay, but this is the bad news or the bad part. This is the extra term that appears when we consider SU local. Okay. Let me just do one thing. So, I will just pull out the G so that I can write out something. I have done nothing, I have just written a GG inverse. Okay. There is a reason for doing this, because I would like to study the structure of this object. What is this object? Okay. So, we need to understand this. So, consider G inverse d mu G. So, now again we will do it like we will repeat what we did with our with the U1, and okay. So, let us study this guy, and let us take G to be just e power I theta 1 of x sigma 1 half. Okay. We take this, and so we need to compute d mu of G. Okay. So, let us do that. If you are cavalier about things, we would have thought we would write something like this. well, this will work, still work. So, this is what you would get, I am by 2. So, this is what we get, and if you work with, and this is nothing but G, okay, and if so, we need to work out what G inverse d mu G is. So, G inverse will come and cancel this, and I end up with I d mu theta 1 of x sigma 1 by 2. Okay. So, you can see this is exactly what we saw in the U1 case, except the structure constant sigma 1 is floating around, sigma 1 by 2, not the structure constant, sorry, the generator of the Lie algebra. Okay. So, this is where the non-abelian, so there now the if I did the same thing with theta 2, there would be no problems, again the same thing will go through. Okay. If I did it with theta 3, again it will go through, but if I do with all of them together, then things do not, the non commutativity comes in. So, let us see what happens. So, let us now, so this this looks nice, this looks exactly, when I turn on only one of the thetas as local, it looks exactly like the U1 case, except we learned one more lesson, that you have to put this t. So, we are fine in that sense, and so roughly you would have thought maybe delta a mu of 1 should be minus of whatever that thing is, right, minus I d mu theta 1 we should write something like this, is what we would have thought, correct. But this turns out to be not quite correct, the reason being that things are non commuting. So, what we will do now is, instead of taking these special examples, we will take the full G inverse d mu G. Okay. So, let us now consider the full thing, that was just a toy exercise. So, I will put a question mark here, consider when all thetas are non zero. Okay. So, now we have to write G equal to e power I theta a of x okay, and we go back to the basic definition. Okay, what was the basic definition, which is expand the power series. For what I need to do, I need to work at least to second order, that is where things would run into trouble. Okay. So, I am pulling out these parameters, but sigma a sigma b is not generically equal to sigma b sigma a. So, I have to be careful on that, but these theta parameters, of course, they are just numbers, they commute with each other. Okay. So, now let us so now let us take derivative of this with respect to G. So, the first term of course will look exactly like what we wrote out here, but the next I want to keep track of the second order piece as well. Okay. So, I get 1 goes away, I but now I have two ways of doing the derivatives, okay, and I get two terms, yeah, okay, and let me just keep this next to each other just for the heck of it. Okay. The temptation here would be to say that look, these two are the same, okay, and I can get rid of the half. Yeah, but there is a problem. The problem is that or equivalently you might think, so the question is, can I let us do something, maybe I can pull out this d mu theta of this thing. Okay, I will try to pull it out, but then first thing is this is a half, this I can pull out, but this I have to if I want to pull this, you may think fine, I can relabel this, I can, this dummy index I can call this B and I can relabel this as A, but it is on the other side, so I cannot pull it through. So there is not a simple way of writing this guy out, it is a whole bunch of terms. You can see if you go to the cubic part, you get 3 terms, okay, and it keeps getting worse and worse and worse. Okay. So what I am trying to say is that this is not equal to okay. Now you can, I mean, but it is true if only one of the theta ones were turned on, then they commute, any sigma 1 commutes with itself. So then these things can be added up and this is, it becomes true. Okay. So now what it tells you is that you have to live with this object, there is no simplification, but now can we make sense of this object is the question. Okay. First thing is this is but whatever you say, you can see that this object here is object which always comes with the sigma A. So one thing you could say, you can say is that G inverse d mu G will be some object which can be expanded as some let us call it alpha mu okay, which is some complicated where plus order theta square. Because the problems came only at theta square. Ah, yes, you can always see this, you can always write it this way. Okay. So the question is now, how do we go ahead defining the gauge field? Okay. So what we do is, so we know several things. We know that we need 3 gauge fields. Okay. And the key is that what we have to do is to, so what I will do here is try to write an object which I will write A mu. Okay. I will explain what I mean by this, which has the following property, that it changes delta A mu, rather no let us write it this way, A mu prime is equal to I will write something and then we will sort it out. Yeah, and there might be factors of I, and I may also have to invert these things. So instead of writing inverse, I should write dagger, because we are assuming that these are okay. Suppose we have something like, we write a transformation, okay, and we define d mu of phi. Actually, let me not even let us work it out. I think that is the best way. Let us write something like this, d mu of phi should be covariant derivative of phi, okay. And similar to what we did, I will write something like this, a mu dot phi. This is just definition. Okay. Except unlike the u1 case, this will be a 3 by 3 matrix valued thing, sorry 2 by 2 matrix valued object. In fact, it will be a Lie algebra valued object, we will fix that. So, what we want, and this should have the property, and d mu of, it should be such that d mu of phi prime, the prime here is indicated that A can also will transform exactly like it did, d mu of phi prime should be equal to g dot d mu of phi. This is our requirement. Okay. This is our this will, so this will fix or determine how a mu transforms. Okay. So, let us do that. So, we start with this guy and then try to equate it to this. So, d mu prime of phi prime will be d mu okay, and this will be equal to, so now there will be d mu acting on this. So, let us write out first the good part, which is g goes through g so this is the part due to the first two. Is it okay now? Thanks. And now this would be minus I, we do not know how this transforms, but we just write that is all. Okay. And I am taking care that I should not, there is no way, I do not know if I can take this through. Okay. So, now the question is this equal to, we need this equal to g dot okay. Now, we get the rules, we can see now that so this term cancels with this, but all the others remain. So, let me just write it out and get rid of the phi from the story, that is what I need to do. Okay. So, let us look at this. So, we get, so what we need is d mu of g minus I prime minus g should be equal to okay, this is not written in a nice manner, but we will massage things around and get it to what we need. Okay. So, to do that, what I will do is I will multiply from the right hand side by g dagger, so that I get rid of this I g dagger. So, the I goes away, and then I will take this to the other side. Okay. So, I am rearranging things, I do two things in one. So, what we get from that is a mu prime will be equal to g a mu g dagger, and this will come to the other side, and I needed to multiply with an I this is how it should transform. Okay. So, now let us check if this makes sense. Okay. First thing is suppose we go back to the u1 example where g is just now e power something, then g and g this will commute, everything goes through, everything is abelian. So, g goes through this a and g dagger is 1, everything commutes. So, this goes off and this becomes precisely the e I mean it becomes d mu of theta as we saw. But now you can see, so this is a very natural generalization of this. Okay. Now this but the thing here is we can simplify things a bit more. We can write we can do two things. Okay. So the thing here is let it remain this way. Yeah. So suppose we expanded a mu, it's valued in the Lie algebra. So I will write this as a mu a sigma a by 2. Okay. Then this will, you can rewrite. So what you will see here is so this shows that you will have, these are the 3 gauge fields. So let us see how this matrix looks like. So let me write out. So let us take the first the case of a mu 1. Okay. So this crypt A actually represents this. The 3 guys will come, and the simplest way to check is this correct is to do exactly, you switch off, if you switch off each one of these guys, you switch off A2, 2 and 3 and see what you get. It should reduce to the u1 and you will see that all these things work perfectly. Okay. Now the only tricky part which I have not shown, but sort of you can see from even here you can see that so let us, let me one part which I have not shown is that g inverse d mu g. Okay. Here g dagger, you may little be also worried about why is it that d mu is acting on the first term and second term while here it is the other way. You can use the neat identities like this and take derivatives of this, play with various things, rearrange things you can. Okay. So we just write whatever is natural to our computation, that is what I wrote. So let us come back to this and see what is the, if I pulled out, if I tried to pull out something like this, what remains on the other side. So you see here I have to write a 1 here, but then I have to subtract a half. So what I will get here is the commutator of sigma a and sigma b, which is again an element of the Lie algebra. So all I am saying here is that I can always write g inverse d mu g as an element of the Lie algebra, always. I am not proving it, but it's at least a second order I am proving it, but it is true to all orders, you can prove that. So in other words which is consistent with our intuitive observation that you require only 3 gauge fields, because if I took an arbitrary 2 by 2 matrix, then there will be 4 independent elements. Okay. But here that is not true. Okay. And this is summation. Okay. So now one of your exercises will be starting from this work out how these guys transform. Okay. That is one thing. And the second thing here is that I have nowhere assumed that g is small. This computation I have not assumed that g is small. If you assume g is small, you should recover this. Okay. Again this is part of your assignment. So this is so now we have a covariant derivative and which makes it transform properly, and so now it just takes, it is a matter of going here and replacing the Lagrangian, which is now not on this board, replace all the derivatives by covariant derivatives. Is that clear? Okay. And one more point I want to make here is these fields a mu are taken to be real vector fields, not complex. Just remember that they are real vector fields. So when you are doing the star guy, those things will work in a normal way. Okay. So so of course the natural thing to ask is what is the analog of the field strength, and we use the definition which we used, it was the abstraction to commutativity. Okay. So, that is our next step, but right now I will stop here.